Okay, so starting chapter 10. Chapter 10 deals with working with different operations on equations, on functions. And we're going to start by looking at sum and differences between two functions and the graphs of those functions. So if we consider the functions f at x and g at x, part A says to determine the equation of h at x, which is f plus g at x. So what f plus g at x means, it means you're going to add the functions together, f at x plus g at x. So f at x is 2x plus 1 plus g at x, which is x squared. And normally we would write that in order of descending power, which gives us that expression there. Then it asks us to graph all three of these functions. Okay? So f at x is the line 2x plus 1. So that's in slope-intercept form. It has a y-intercept of plus 1 and a slope of positive 2. And remember, slope is rise over run, so we can rise 2 and run 1. Rise 2 and run 1. And we can do that multiple times. We can also rise negative 2 and run negative 1. Negative 2 over negative 1 is still positive 2. So we can do that multiple times as well. We're good right now, thank you. Right, so there's that graph. Then we also graph g at x, which is x squared. So that's a quadratic vertex at the origin, 0, 0, 1, 1, 2, 4, negative 1, 1, and negative 2, 4. And we can do one more point here, 3, 9, and negative 3, 9. Right, so there's that graph there. So that's the graph of g. And finally, we want to graph h, which is x squared plus 2x plus 1. You with us, Sant?
Yeah.
So you could certainly set up a table of values for this one if you wanted to. However, if you factor it, the factors would be x plus 1 all squared. Two numbers that multiply together to get 1 and add to get 2 are positive 1 and positive 1. And so if we look at this in comparison to y equals x squared, we can talk about this as a transformation of y equals x squared. Compared to y equals x squared, that positive 1 tells us the h value. Remember, whatever happens to the x also happens to the x minus h. Our value of h here is negative 1, which means that compared to y equals x squared, it would be shifted 1 unit left. All the points on y equals x squared are shifted 1 unit to the left to give us y equals x plus 1 all squared. All the points get shifted 1 to the left. So this point of negative 3, negative 9 becomes negative 4. Positive 9, sorry, not negative. Negative 2, 4 becomes negative 3, 4. Negative 1, 1 becomes negative 2, 1. 0, 0 becomes negative 1, 0, and so on. All the points shift 1 to the left. And here's that graph. It's going to be congruent to y equals x squared, meaning it has the same shape. It's just shifted one to the left. Okay? So that would be one way to sketch the graph of h. It's a comparison to y equals x squared. And we can only do that because we were able to factor it and then talk about it in terms of a transformation comparing it to the graph of y equals x squared. But there's another way to sketch the graph of h, and that comes directly from your two functions f and g. So let's look at this in terms of a table of values. So if we have these values of x, -3, -2, -1, 0, 1, 2, and 3. So these are x values, and we're going to get the y values for the first two functions. So the y values for f, which is 2x plus 1. So the y values, or the x value, be multiplied by 2 and then increased by 1. -3 times 2 is -6, plus 1 is -5. 2 times -2 is -4, plus 1 is -3. 2 times -1 is -2, plus 1 is -1. 2 times 0 is 0, plus 1. 2 times 1 is 2, plus 1. And you should have noticed a pattern here is that x is increasing by 1, our y values are increasing by 2 because that's the slope of that line. That's the rate of change. So we could continue that if we wanted to. So there's are the y values on y equals 2x plus 1. What about the y values on y equals x squared, which is what h is? So in each case, the x value will be all squared. Bless you. And now the y values on h, which is x squared plus 1. And remember, that came from adding f at x and g at x together. That's where we got that equation from. But what we did is we said, by comparing that equation for h to y equals x squared, we saw that we could take the graph of y equals x squared and just shift it one to the left because x plus 1 all squared compared to y equals x squared has an h value of -1. Okay? So we shifted it one to the right. So if we take the point where x is -3, the value of y is +4. If we take the point where x is -2, the value of y is +1. If we take the point where x is -1, y is 0. If we take the point where x is 0, y is 1. The point where x is 1, y is 4. The point when x is 2, y is 9. And we don't have the point where x is 3 on that graph, but that's okay. And now, if you look at the y values from 2x plus 1 and x squared, and you compare them to the y values for f at x plus g at x, you should notice that the y values from f and g would be added together to get the y value for h. Right? -5 plus 9 is 4. -3 plus 4 is 1. -1 plus 1 is 0 in every case. And so the y value for h when x is 3 will be the sum of 7 and 9, which is 16. The y values are added together to give you the y values for the new function, which makes sense because that new function came by adding the two equations together. So it makes sense that the y values would be added as well, because y equals f at x and y equals g at x. So f at x and g at x are added together, so the y values are added together. Thank you. Right? So what this does is this would eliminate really drawing the two graphs of the first function. You could generate a table of values for the first two functions though. And then if you want to find a new function which is found by adding the two functions together, all you have to do is add the y values together. Okay, so question C says state the domain of h at x. Well, the domain will be going from negative infinity to positive infinity. There's no restrictions on x. And it says determine the values of f at x, g at x, and h at x when x equals 4. So that's not on our table of values, but that's okay because we can use the equation. F at 4, remember that function is 2x plus 1. 2 times 4 is 8, plus 1 is 9. G at 4, well, g at x is x squared. 4 squared is 16. H at 4, h at x is x plus 1, which is 5 all squared, gives us 25. And again, if you add 9 plus 16 together, you get 25. So that just reconfirms what we talked about before. So this also makes it quite easy to sketch the sum of two functions if you have those original graphs to begin with. You just take corresponding points on the graph, meaning they have the same x value, they're going to have different y values, add the y values together. And that'll give you the points on the sum of those two functions, which is what we're asked to do here. So let's start with the values when x is negative 4. You'll have a y value of 1 and a y value of negative 3. 1 plus negative 3 is negative 2. So that's that point right there. The x value is the same. It's the y values that are changing. The next point, when x is negative 3, you'll have a y value of 0 and a y value of negative 2. Added together, those also give you negative 2. The next point, the y values are both negative 1. Negative 1 plus negative 1, again, is negative 2. The next point, when x is negative 1, you'll have y values of 0 and negative 2. They add together to get negative 2. And we'll do that with all these. 1 plus negative 3 is negative 2. 2 plus negative 4 is negative 2. So you're seeing a pattern here, and that's going to be consistent. 3 plus negative 5 is negative 2. You see, because the two original functions are linear, they're changing at a constant rate, then their sums will be constant as well. And so in this case here, our graph is a line. That is the graph of f at x plus g at x. All right, now in this case, it's changed. M is f minus g at x. But the principle will be the same. In this case, you will subtract the y values. Now, when you're adding them together, it doesn't matter what order you follow. But when you're subtracting, order absolutely matters. It has to be the y value on f first minus the y value on g second. So f, if we go where x is negative 4 and start with f, it's going to be negative 3 minus 1, which is negative 4. The next point, you're going negative 2 minus 0, which is negative 2. So this is not going to be a horizontal line like the last one. The next point, the two y values are the same. They're both negative 1. When you go negative 1 minus negative 1, that becomes negative 1 plus 1, which is 0. The next point, when x is negative 1, remember you're starting with f first. So now f is above g. It's 0 minus negative 2, which becomes 0 plus 2. The next point, when x is 0, it'll be 1 take away negative 3, which is positive 4. The next point, when x is 1, It'll be 2, take away negative 4, which is positive 6. So this is also a line. Once again, our original functions are linear, and a line has a constant rate of change. The differences between these two graphs will also be linear. There will be a constant rate of change. It's just that this line has a slope, where the one we looked at earlier didn't. And in this case, we're subtracting, and you have to remember to keep the order. It's always f minus g, because that's how the equation is written. So order absolutely matters when you're subtracting the functions, but not when you're adding. Example 3, consider those two functions. Determine the equation for f minus g at x, which again is f at x minus g at x. F is the root of x minus 1. And you're subtracting all of g, so we'll put it in brackets. That's you're talking about an embedded function. That's not what we're talking about here. You got to go f at x minus g at x. That's what the equation tells us to do. Oh, I'm sorry. I apologize. I misheard you. Okay, thank you. All right. So that would be the equation. So you're given the graph of y equals the root of x there, which is f at x. You're given the graph of g at x, which is x minus 2. Now you want to sketch on the same grid h, which again is f take away g. So order matters. You got to start with f first. Now, f has a restricted domain. X has to be greater than or equal to 1. That's where the graph starts. So that's where you have to start for h. You can't get any values of f less than negative 1, positive 1, excuse me. So we have to start at that point there. That means you're going to have a restriction on the domain of h. H can't start any lower than positive 1 either. But in each case, we take the y values for f and subtract the y value from g. So for the first one, it'll be a y value of 0 minus a y value of negative 1. 0 minus negative 1 becomes 0 plus 1, which is positive 1. You can also only use points that you know where they are. Like, for example, we probably can use when x equals 2 here, because it looks like on f, y is 1, and for g, y is 0. So 1 take away 0 is 1. I put that first point in the wrong spot. It's 0 take away negative 1, which becomes 0 plus 1. So it'll also be at y equals 1. The next point we can probably use would probably be not till x equals 5, because we can say what the y values are. The y value of f is 2 minus a y value of g, which is 3. 2 minus 3 is negative 1, which is right there. So the next one we can do probably won't be until it looks like we get to around x equals 10. The y value on f is 3. At g, the y value on f is 8. 3 take away 8 is negative 5. So approximately right there. Now you might think that this first section is a horizontal line. Well, let's check and see if that's true. If we estimate our values when x is 1/2. So we'll estimate the value on f to be, let's say, approximately 0.8 minus the value on G, which we'll say is approximately negative a half, approximately. So you're going to get 0.8 plus 0.5, which will be 1.3. So it actually comes above those first points that we had graphed. And then the remaining section will be linear after that, because these points all line up. But then after that, the graph has a bit of a curve shape to it. And it might be two straight sections. We don't know for sure. But between those first two values, where y is 1, we've seen that the graph does go up a little bit. And then it'll come back down to that point. So the domain of h would be from 1 to positive infinity. The 1 would be included, infinity is not. Use the graph to approximate the range. Well, again, we said that this point here came up to about 1.3. So we would estimate it from negative infinity up to approximately 1.3. But that is just an estimate. Right? We don't have the original equations. Actually, we do have the original equations. So we could use our calculator to write the new equation and get it that way. So our new equation was the root of x minus 1. And then outside that was a negative x and a plus 2. If we graph it, and let's go zoom decimal, we might get a better look at the graph. And we're going to find the maximum point, second function trace. Number 4, which is the maximum. I'll set my left boundary at 1 and my right boundary at 2. And it's actually, it looks like it's closer to a maximum of positive 2. Okay. So because we had the original equations, we were able to do that. The question did say use the graph to approximate it. So using the graph on the calculator was a better approximation. Okay? But we could only do that because we had the original equation. All right. So once again, we're given two functions f and g. Determine the equation of f minus g at x. So that'll be f at x minus g at x, which is the absolute value of x minus x plus 5. When you subtract all of g, it's like there's brackets around it, and the negative sign in front changes all the signs inside. And now we want to sketch h, and again, order matters. In every case, we have to go f first minus g second. So the first point we could probably use here looks to be about negative 3. A y value of 3 minus a y value of negative 8 becomes positive 11, which we don't have room for on our graph. So let's try when x is negative 2. It'll be 2 minus negative 7, which is plus 9. And we can kind of guesstimate where that one will be. When x is negative 1, it'll be 1 take away negative 6, which is plus 7. When x is 0, it'll be 0 take away negative 5, which is 0 plus 5. 1 take away negative 4, again, is plus 5. 2 take away negative 3, plus 5. 3 take away negative 2, plus 5. The rest of this graph will be horizontal because for this part of the graph, f at x is increasing at a constant rate, and so is g at x changing at a constant rate. So their difference will change at a constant rate. And we've established what that difference value is. It gives us plus 5 every time. So one arm of the graph will go like that. The other arm of the graph would go like that. And these two have arrows on the ends because there's no restrictions on the domain. Both graphs go to the left forever. So the domain of this is all real numbers. Goes left and right forever. So negative infinity to positive infinity. But the range of h is not all real numbers. It has a minimum value of plus 5 as it goes to the right. As it goes to the left, it's going up to positive infinity. Yeah. No. F minus g at x. That's function notation. So part D asks, is f minus g at x equal to g minus f at x? So we already have f minus g at x above. We've already calculated that. It is the absolute value of x minus x plus 5. But what is g minus f at x? Well, that means g will be first. It'll be x minus 5 first minus the absolute value of x. If you rearrange that in the same order as the previous equation, it'll look like that. And obviously they're not the same. But they are in fact opposites of each other. You see, if you take out a common factor of negative 1, you'll have the absolute value of x minus x plus 5. And what's inside the bracket there? Let me draw that better. Excuse me. What's inside the bracket does equal what f minus g at x is. So it's actually the same as f minus g at x with a negative in front, a negative 1 in front. And remember, thinking about transformations, a negative 1 in front of a function means that it's reflected over the x-axis. So g minus f at x will equal f minus g at x after a reflection about the x-axis. Okay? All right, so we'll stop there. I want to make sure you have lots of time to work on your quiz. Is there an assignment in your booklet? No. 10.1? Yeah, I think there is, eh? What's that page right there that you're looking at? That's 10.1 assignment, isn't it? Yeah. So you can work on that for practice if you want. I'll put the solution on Google Classroom for you, but first you're going to write your quiz on Chapter 9. Okay?